Finally, let's consider the transport of charge through a conductor. So I have the z-axis defined this way, and you can see that there is a uniform electric field epsilon pointing in the positive z direction, which causes a current density to flow in the positive z direction. So we have a system, so we're considering a system which has containing charged particles that are free to move. So in the case of a dilute gas, these could be ions in the gas that are free to move. And we have a epsilon uniform electric field that points in the positive z direction, and there is a current Jz that flows in the positive z direction. Jz is the mean electric charge that is crossing a unit area, so it's a current density per unit time. And it's in the positive z direction. So this is called current density. It's actually a charge flux, if you wish. So if epsilon was 0, if we had no electric field, that would give us a 0 current density, no current flow. But on the other hand, if I have a small electric field for small epsilon, we find that the current density is directly proportional to the electric field with a constant sigma e. This linear relationship between the electric field, small electric field, and the current density is known as Ohm's law, and sigma e is our electrical conductivity. Now let's consider a dilute gas of particles with mass m and charge q and epsilon in the positive z direction, so that we have a mean value of the z component of the velocity of these charged particles. So we have a dilute gas particles with mass m, so it consists of particles with mass m and charge q, epsilon applied in the positive z direction, and mean z component of velocity Vz bar in the presence of a uniform epsilon in the positive z direction. So the current density Jz is the number of charges per volume n multiplied by their mean speed in the z direction and multiplied by the charge per particle. So this is a number per volume multiplied by length traveled per time multiplied by charge. So this basically gives us number per area per time times charge, which is the current density Jz. And we can use Newton's second law, the net force acting on a charged particle in the z direction, m dvz dt, its acceleration, is q, its charge, multiplied by epsilon, the electric field. So basically this equation is F equals ma. Electric field is by definition force applied per charge. So multiplied by charge gives me the net force acting on it, which is ma. And the solution to this equation, so this is my equation of motion. The solution to this equation for the z component of its velocity vz is vz at time t is equal to 0 plus q epsilon over m t. Well, if you take a derivative with respect to time, you will see that dvz dt will be q epsilon over m. So indeed, this is the case. And if I take the time average of this equation, so if I take the time average, I will get Vz bar, the mean value of the z component of the velocity, is q epsilon over m times tau plus the Vz value at 0 average. So this is basically, tau is the mean free time, the time between two successive collisions, and that's the time interval in which we can have a change in the velocity. And after each collision, we come out with random direction of velocities. So this is going to be 0 with no applied field. So after each collision, we have basically a random velocity distribution, and Vz0 will be, the mean value of Vz0 will be 0, and then in the time interval tau, we're going to have a mean speed q epsilon over m tau. So tau is the mean free time. So the effect of each collision is to randomize the direction of the velocity. So therefore I will find that Jz is equal to, it was given by nvz bar q, n q multiplied by vz bar, which is q epsilon over m tau. So it will be equal to n q square tau over m multiplied by epsilon. So I recognize that the electrical conductivity is n, number of charges per volume, q square, charge per particle, multiplied by mean free time tau, divided by the mass per particle m. Alright, so basically this gives me the end result for the electrical conductivity. Now we can basically see that this result comes from having a uniform electric field inside a dilute gas that contains charged particles, so it has ions in it, and this uniform electric field will cause a current density, mean electric charge per area per time, which is given by sigma times the electric field according to Ohm's law. This is true for small electric fields, and the current density or the charge flux is nvz bar q, and you can see that Vz can be obtained by the equation of motion. Solving the equation of motion, F equals ma. F is q times epsilon for charged particles. I'm neglecting any other effects. Well, we're assuming ideal gas that has no interaction forces between the particles, and we're assuming that the only force of interest here is the or significant force here is the electric field, uniform electric field epsilon. So after each collision, we'll come out with a random velocity direction. So Vz bar at time t is equal to 0 is 0, and the mean value of the Vz is q epsilon over m tau. If you substitute this into the equation for Jz and Vz bar q, we obtain electrical conductivity nq squared tau over m. Well, let's summarize what we have learned about the transport in a which is a non-equilibrium situation. We talked about the mean free path initially, so let's have a quick review here. We talked about the mean free path, which we found to be 1 over square root 2 n sigma, where n is the number of molecules per volume, sigma is the total scattering cross section, and using our hard sphere approximation, so n is number per volume, sigma is 4 pi a square, where a is the radius of a molecule. And we talked about the viscosity of a dilute gas, which we found to be 1 over 3 and v bar ml. So here we have momentum transport, and this n is again capital N divided by v, number of particles per volume. V bar is the mean speed, m is mass per particle, and L is the mean free path. And then we talked about diffusion process. Diffusivity we have found to be 1 over 3 v bar L. We talked about thermal conductivity, which we found to be 1 over 3 and v bar CL, where C is the derivative of epsilon with respect to temperature at constant volume. It is the heat capacity per particle. And then we have talked about electrical conductivity. So for electrical conductivity sigma, we found nq squared tau over m, where tau is our mean free time. So in the case of the diffusion process, we have mass transport. So we're transporting mass, we're actually transporting particles. In the case of thermal conductivity, we have energy transport of energy transport. And in the case of electrical conduction, we have charge transport. So we have talked about 4 different transport processes that are examples of non-equilibrium situations that gave us these simple results, and it also gave us some information about temperature dependence, pressure dependence, concentration dependence, etc. of these parameters using a very elementary kinetic theory.